Good evening. I am going to cover the principles, geometries, configurations, derivations, and applications of antenna arrays. So let's get started. In this slide, I will be talking about the principles of array theory. Let's say we have a cloud and it has some water, and the water falls off from there into the pond to create ripples, and this ripple creates waves, and the waves are analogous to the sinus waves, right? In the figure 2, we have a radar system. If the radar system tries to propagate signals to detect how much further uh, the other object from the radar system by sending it in all directions. How can the radar system detect the object is uh, which one, how much farther it is? So it's better if we configure the antenna of the radar system in such a way that the beam width is much narrower and the directivity is much higher. Then the aeroplane, for example, can be detected, and its how much further can also be obtained. So the buildings and other objects that flying from here and there can be detected and can be considered into our calculations. So to have the narrow beam, we usually consider two configurations. First, a large and huge antenna, and there are several antenna elements that are placed in a certain certain arrangement, and that is called the antenna arrays. There are several problems with the large sized antennas, uh, such as the increased cost and the mechanical constraints involved. So in order to improve these things or compensate, we need to have an antenna array, and the characteristics of antenna array are high directivity, narrow beams, low side lobes, steerable beams, higher antenna gain, and shaped antenna patterns. In order to get the main lobe or the main narrow beam, we have to think about the diffraction principle and the interference among all the antenna elements in a linear antenna array. Each one of these antenna elements tries to send signals in a certain direction. There is a probability of getting overlapped in here, here, and here as well. In this direction, we have the main lobe, and in other overlapping places, we might have the back lobes and the side lobes. In figure 2, we can see that a resultant vector sum of the induction field has been drawn. After changing the time, amplitude, and phase of each one of these elements, we may change the direction of the resultant induction field or the main lobe. In the diagram 3 and diagram 4 and diagram 5 as well, we can see that two drops of water are falling, and that create ripple in the bucket of water. This main narrow beam is perpendicular to the nozzles from where the water is falling. We are thinking about these nozzles as two identical array elements. Okay, and this diagram 4, we have four arrow signs. In this arrow science, we can visualize that there is no spherical waves propagating. In figure 5, there are side lobes. They are created basically in this position and this position. As we have already discussed in the previous slide, that after changing the phase, time, and amplitude of each one of the elements, we can easily get the resultant vector sum of the induction field or the main lobe in other directions through the digital signal processing. Although the direction of the resultant vector sum of the induction field or the main lobe is considerable, the array beam pattern or the shape of the array beam pattern can also be taken into account. This can also be done by several ways. Among all of them, we must consider the modification of geometries, modification of distance, and modification of excitation of the amplitude phase. Here we can see 4 arrangements: linear array, circular array, planar array, and conformal array. This conformal array can also be called as the spherical one. Usually we see these two types of arrangements in our practical life. When we change the distance of each element, we can also change the beam pattern or the size of it. And lastly, after changing the excitation with this attenuator and the phase through this phase shifter, we can easily change the beam pattern in the far field region. Now we have to deal with the electric field and power density of an antenna array, and these two are the most important parameters of all time. The equations for these two parameters are given by these two equations. Uh, these are the elements, each element's electric field and the power density. The first factor is known as the spherical propagation factor, which depends upon the range r, and this range r can be defined as the distance from every element to the observation point. But in the far field approximation, we are considering the wave is parallel to each other, so the distance or the range will be the same, r. In the second factor, Fe, that depends upon the direction of the electric field intensity. Now in this equation we can see that here in the denominator we have one symbol, that is eta naught, that is known as the intrinsic impedance, and intrinsic impedance is equal to 120 of pi. Okay, and the geometry relative to the observation point is shown here, and the rays between the elements and a far away observation point are approximately parallel, is shown here. So the distance between the interspacing between these two elements are identical, and the whole distance from the bottom one, the bottom element to the upper one is L. That is nothing but L minus 1 into D, and R changes if the far field approximation is not taken into account. But here the distance from this one to that one is id, that is equal to z. We are considering it. So if we take the trigonometric approach, we can easily say that ri that one is equal to r naught minus id cos theta. That is, they are all close enough. Okay, so that's it. In the previous slide, we have seen the electric field and the power density of every antenna element. But here we are considering ith element's electric field. The electric field expression of ith element can be given by this equation, where Ai is the complex feeding coefficient, and the complex feeding coefficient is constructed by Ai into exponents of j psi I, where A is the amplitude and phase phi I of the excitation of the electric field, and this gives rise to the EI relative to the reference excitation. In practice, excitation of one of the elements is used as reference. Note that RI and AI may be different from element to elements in the array, but phi E is the same of all of them because they are all identical and hence exhibit identical directional patterns. Now we are taking the integration of all the energies or the electric fields of every element. Now we are taking this equation into consideration. Now as we have already said that EFE is identical and it depends on the beam pattern, so it is taken to be a constant, and the rest of them are integrated here, and these four equations have already been discussed in the previous slide, where the far field approximation was considered. Now it's time for us to think about the electric field and the power density of the whole antenna array. The equations for them are given here and here. The first two factors are considered to be constant, whereas the last factor is a variable. R naught and ID, these two have been used because of the far field approximation. These expressions are substituted in this power density equation. This factor is the power density of every element in the antenna array, and this can be written as this, and it goes as it is. This is called the array factor, and the array factor is defined as a function of the positions of the individual elements and their feeding coefficients, but not a function of the specific type of radiators used. There is a thing that needs to be considered. First thing, the array factor represents the far field radiation intensity of nth elements. Had the elements been isotropic radiators, so the array factor with complex feeding coefficient is shown here. What does it mean? It means that AI, that is the AI is replaced by a small ai of E phi I, and all remains the same. The power density of antenna array with array factor uh, can be obtained by the pattern multiplication principle, and it allows us to find the far field power density of the antenna array by first computing the far field power pattern with antenna elements replaced with the isotropic radiators, which yields the array factor Fa, and then multiplying the results by Se, the power density of a single element, which is the same for all the elements. So that's that. We can have the equations of the electric field and power density. There are a number of benefits of using antenna arrays in cell tower and mobile communications. We incorporate the antenna arrays into our network to overcome the limited channel bandwidth, increasing the channel capacity. That means that number of users can be increased by employing these antenna arrays, then extend the range of coverage through that, because we can easily steer the beam, and the directivity can be higher, compensating the aperture distortion, then reducing the multipath fading. Can be explained as the when a user moves from one base station to the another, there is a chance of uh, being hands off. So due to that, there is a loss of signals and communications. So to compensate that, antenna arrays must be added to the system. Then lastly, to reduce the system complexity and cost, there is no alternative to the antenna arrays. Here goes another advanced application. If we add the antenna array into our car somehow and drive the car on the road, we can easily sense off the signal towards the obstacle or other cars on the road, and that reflects off and comes back to our car, and so that well in advance we can avoid the destruction, right? So that's how the automotive industry are thinking about incorporating antenna arrays in a significant amount nowadays. That's all for this presentation, and thank you for listening.